eigenvalues, the EIs. So V of R is the eigenvalue of the Schrodinger equation. And the EIs are the eigenvalues, the energies of the whole molecule, including the motions of the atoms. So this V of R is holding the atoms fixed at one particular value of the geometry. So for example, if I have water, I can have geometries that are like this. I can have geometries that are like this. All different geometries. And they each have different energies, depending on how long the bonds are and what the angles are. And so V of R is the energy of this one compared to the energy of this one. And each of those is a solution of the Schrodinger equation. So it's an eigenvalue of the motions of the electrons. But when I do the calculation, I hold these H's, O's, and H's fixed at the capital R position. And so this corresponds to R1. This corresponds to R2. And there's many, many different choices of capital R. And each one is a different geometry of the atoms. For each of those atoms, the atom geometries, the electrons do whatever the heck they want to do. And they get a V of R. And I get that by using the quantum chemistry program, solving the Schrodinger equation to get the V of R. Then after I get the V of R, I need to figure out what is really the kind of average energy of the whole molecule, considering all the possible geometries you could take, because it's vibrating around and fluctuating. And that's what I'm going to talk about now. The key approximation that's used to get the EIs is separability. So the true operator that gives the energy is a function of the positions of all the atoms and the motions of the momenta of all the atoms. And that's really complicated if you have a big molecule. So actually for water, it's not so bad because there's only 9 atom positions, 3 XYZs, right? An XYZ for each of the 3 atoms. But for a big molecule, like an amino acid, it's really a lot of coordinates. There's a lot of different positions of the atoms. There's a lot of atoms. They all could be different places. And so V of R is a very high dimensional function. And the key to making it possible to figure out the energies is to approximate the Hamiltonian as the sum of a translational Hamiltonian, a rotational Hamiltonian, and vibrational Hamiltonians. And in fact, to subdivide this one into n different vibrational Hamiltonians for different vibrations. And if you can do this, if you have an H that can be written this way, it turns out that each of these have their own energy eigenvalues. So the translation is called the Hamiltonian, the operator for translation. It has certain energies that correspond to it. The Hamiltonian for the rotation has certain energies, and the Hamiltonian for each vibration has its energies. And so this is how to simplify the problem. Instead of having all of the coordinates coupled together, assume that they're separable. To some extent, they really are separable. And other ones, they're mostly separable, but there's some small terms that couple them, and we just erase them. And just say, let's ignore them for a minute, so we can actually get solution. And that's what the rigid rotor harmonic oscillator is about, the approximation. So first we say, let's assume that it's a really ideal gas, and when the molecule translates around, it's not even aware that there's any other molecules in the container. And if you do that, you can get the solution of a single molecule moving by itself in a vacuum in a certain size box. And this turns out to be the eigenvalues of the translational Hamiltonian. And they're Planck's constant squared, 8 times the mass times the dimension squared. And then it has some quantum numbers. And the Q is you plug this E in and divide it by KT. And that's the thing you have to add up. And this sum is actually, nobody knows the analytical form for this sum, but it's pretty close to this integral. So there's like a way, integrals and sums are kind of close to each other if your graininess is not too much. Just like we did like rectangle rule when we were in high school to evaluate integrals as a sum of rectangles. Same kind of idea. And so here we can say, well, this thing looks kind of like a rectangle rule for this particular integral. And this one we can actually solve analytically. And here's the solution. So therefore we say that the Q for the translations is approximately equal to this thing. And it's just as the mass, Boltzmann's constant, temperature, Planck's constant, and the volume of your container. Yep. Here, X, Y, Z.
Oh, at the very top.
Oh, yes.
Okay.
Should not be X, X, X. Yes, it should be X, Y, Z. Thank you. Good catch. Okay. So that's the translational one. Remember, I separated my Hamiltonian into different parts. So I just did the translational one. It's pretty simple. The other one's a little more complicated. For the rotations, for rigid molecules, it turns out that the vibrations barely move the atoms at all. They only move very small amplitude at normal temperatures. And so they're very small amplitudes compared to the bond lengths. So basically the bond lengths stay approximately constant during the vibration, and therefore we can just start by assuming that there's a zero order picture that is completely constant. So it's like a tinker toy. You ever made those little molecular models with like a little tinker toys, the balls and the springs or the balls and the sticks? Just imagine it's like that. So we're going to pretend the molecule is like that, and then figure out how that solid object would rotate.
So the frequency is different of vibration and rotation.
Yeah, the frequencies of vibration are usually much higher than the period of rotations. But also we're neglecting actually the Coriolis force. In reality, there's a Coriolis force that if you have a rotating body and it's vibrating on top of it, it would feel like a Coriolis force that causes like the wind patterns in the earth and stuff because of Coriolis. We're going to just cross that term out. It's too confusing. And so that's one of the many small terms we're going to throw away. And then this rigid thing is that we're also neglecting what's called a centrifugal distortion, that when things spin fast, they actually stretch out a little bit. And we're not going to worry about that either. So there's a lot of things we're neglecting. But it makes it easy. See, we're in the view of the engineer. We're doing the easiest thing here. Either the engineer or the physicist. It's funny, actually. They both come the same way. Right? The physicists, they say assume a spherical cow. And then they'll go ahead, because they only want the big picture. And the engineer, they want the real answer, but actually don't want to work that hard. So they start making all kinds of approximations too. So that's what we're doing right now. And so for a linear molecule, say hydrogen, H2, this is what the energy levels look like. You can just solve the quantum mechanics equation for rotation. And it turns out to be pretty simple. It's like there's a quantum number for rotation, and that thing basically squared comes in, and you multiply by Planck constant squared divided by 2 pi squared. And it has a moment of inertia in the denominator. This one also leads to a summation that we don't know the exact analytical expression for, but it looks a lot like an integral that we do know. So we do the same kind of approximation we did for the translation for the rotation, and we end up saying that the Q for the rotation is approximately this, where it depends on the moment of inertia, instead of the mass. And there's a little complexity in it. There's a thing called a symmetry number. So for example, when water rotates, some of the rotations make it look just the same because you interchange the two H's. And so because of that, there's like a symmetry number of 2 that shows up in the formula. So that's what the sigma is. But otherwise, this looks a lot like the formula here that we got for translation. You can see you have like 2 pi times mass times kBt over h squared. And here's the same kind of thing. For a nonlinear molecule, there's 3 different moments of inertia in each of the 3 principal axes. And you can just multiply them out, where now you have the square root of IA, IB, IC is like the mean, and it turns out to be the formula. It works all right. Now, because we started by assuming that the vibrations amplitudes are very tiny, that suggests immediately we should do a Taylor expansion in the vibrational motion compared to the geometry. And so what we're going to do is pick the particular value of the geometry that has the lowest energy. Remember I talked about the other day, there's one particular R that gives the bottom of the valley. That's the most stable geometry. So that's called the equilibrium geometry. So if you could, the lowest possible V you could ever get. So let's use the equilibrium geometry as our expansion point, and we'll expand a multidimensional Taylor series around that point. And so if you only keep the quadratic terms in the Taylor expansion, so at that point you're at a minimum of V of R, so the first order terms are gone. There's no gradient. So then you have second order terms. If you keep the second order terms, then it turns out you can find a coordinate system where it kind of diagonalizes the tensor for it gets rid of all the cross terms between all the quadratic terms to make it just a sum of q squareds. So you end up basically, it's a sum of harmonic oscillators. And if I just stop then, I say I'm not going to worry about cubic or quartic or any other terms that might be in the Taylor expansion, but I'm just going to cross them all out and only keep the leading term, which is the quadratic term. Then I get the harmonic oscillator, and the harmonic oscillator you can also solve it analytically. It's a Schrödinger equation. It has a simple expression for what the energies are that are allowed. Oops. This one you can actually evaluate analytically what the sum is, the Boltzmann sum, and it turns out it's exactly this. So this is the expression for the sum up here. The Boltzmann sum of the EIs. If I plug in this expression for the EIs, it turns out that's a type of infinite summation that you can actually have an analytical expression for. And so there it is. And that's it. And we have to do the product of one of these forms for every harmonic frequency. So you have vibrations, different normal modes that correspond to different linear combinations of motions of the atoms. Some of them have high frequency, some of them have low frequency. You have to add up, you have to multiply together a term like this for every different frequency of the 3n minus 6 terms you actually have when you do this. To do this, you need to know what the values are of these new i's, the frequencies. And so for some small molecules, people have measured them experimentally by doing IR spectroscopy. But most commonly, you don't actually know all the new i's for your molecule because there's problems in the experiment. It's hard to actually determine all of the vibrational frequencies experimentally. Some of them don't have any oscillator strength, for example, so you can't see them just in IR spectra. Sometimes they overlap with each other, so it's hard to see which ones you're looking at, stuff like that. So most commonly, you have to calculate them, and you can do that. One way is by just roughly, you can say, well, carbonyl groups usually have frequencies like such and just use that number. That's the rough idea. Some people use molecular mechanics and molecular dynamics, and they would just assume that the force field that somebody gave them was true, and then they would use it to compute frequencies. But of course, that's dangerous too, because where did the force field come from? For small molecules, you can use the couple cluster method that I talked about, and you can get really great vibrational frequencies. It's super accurate, but it's also CPU intensive. So this is typically only done for small molecules, because as the molecules get bigger, as I mentioned, the couple cluster calculations go as the number of electrons to the 7th power. So if I have 10 times as many electrons and the molecules is 10 times as large, it means it's going to be 10 million times longer to compute the frequencies for that one compared to the small one. And so that's really not so good for your CPU budget. This is a really good approach for small molecules, but not really good for big ones. So the most common approach is to do an approximate type of quantum chemistry calculation called a density functional theory calculation. And that calculation is not very CPU intensive, and so you can definitely do it even for pretty big molecules. It's approximate, but it's usually pretty good, but you're introducing additional approximations in the density functional theory. And there's many different choices of approximations in density functional theory that are kind of complicated, and they all have funny acronyms like B3-LIP or MO62X or Omega B3, and there's so many different ones. And there's a whole conference of the density functional people get together and try to figure out which of the methods are the best. And you could just read the papers and they'll give you recommendations. Like today, we think this is the very best one to use. And actually for density functional theories, some of them are particularly good for vibrational frequencies, some of them are particularly good for geometry, some of them are particularly good for spectra, like electronic spectra. So you can read about which one you should use for whatever you're trying to compute. Let's explain how density functional theory works. The Schrodinger equation gives you a way to take a wave function and compute the energy. So it says, if you give me the wave function, I have a procedure to compute the energy of the electrons corresponding to that. But the wave function is a function, as I said, of 3 times the number of electrons, right? It's like if you have 100 electrons, it's 300 coordinate function. For benzene, it's 126 variables, for example. And this is really hard. So it's hard to get, if you ever have to figure out an unknown function of 126 variables, you're in trouble. So a guy named Kohn, who got the Nobel Prize, and I think his student Hohenberg, together made a proof that there is actually an energy functional of the electron density, where the electron density only is a function of x, y, z. It doesn't depend on the position of each electron separately. It's only the cumulative probability density of all the electrons. So this is way simpler because this is a function of only 3 coordinates and this is a function of 126 coordinates. So this is very practical. You can actually find functions of 3 variables. It's not that hard to do it. However, unfortunately, Hohenberg and Kohn's thing was an existence proof. They proved that E of rho existed, but they didn't tell you what it was. This is like the evil thing that mathematicians often do to us. So then Kohn with another guy, Sham, found a way to proceed where they said, we can figure out how to make electron densities that actually are physical by writing them as sums of orbitals, like this. And these are each functions of only 3 coordinates, so that's not so bad. It's not quite as simple as rho, but this is still okay. In the 1980s, people kind of guessed what E of rho could be. Particularly 2 guys, Perdue and Becca, made some really good guesses about how the energy functional must be. So that you knew it existed. It was like this mystery, the great white whale. We know it exists. Somebody saw it once. We're going to find it, or Bigfoot, or something like that, right? We're trying to find the energy functional. And so Perdue and Becca and a bunch of other people spent a lot of time trying to figure out what the heck this functional must be. And they came up with a pretty good approximation of it, a couple of them actually. And so B3LIP and PBE and MO62X are all names of different functionals. And to the extent that these are close to the true energy functional, which we know exists, but we don't know what it is, then they would give you the true energy. And it gives you a way to compute things for not much time. And so all those programs I mentioned, Gaussian, QChem, MolPro, et cetera, they all have ways to compute the energy from using density functional theory instead of using the wave function. You have a choice. When you use these programs, you can decide, do I want the density functional theory thing or do I want the Schrodinger equation thing? And it turns out that they can compute not just the energies, but also the derivatives, d, v, d, r. This is like the force on the atoms. The gradient is, and if you want to find, if you want a contour plot and you're trying to go from R1 to the minimum, if you know the gradient, it makes it much easier to find the minimum. And so that's what these codes compute the gradient with density functional theory. And then you only have to take typically a few steps, and they can find the minimum. And they typically use the BFGS algorithm. I don't know if you guys know what that is. No, anyway, it's a really good optimization algorithm. If you ever take a numerics course, I recommend. Learn about this. So this usually works great. It finds a minimum. There are multiple local minima. So example here, there's 2 minima here and here. And we would call them 2 different molecules. But from the point of view of the math, they're just 2 different minima on this V of R surface. And so if I gave an initial guess it was over here, the optimizer would step down to here and find this local minimum instead of finding this other minimum over here. So you have to give good initial guesses at the geometries. And what happens when you look at this is often it looks like this. So here's one minimum, here's a little valley around it. Often there's another little minimum here, and there's really not much of a barrier between them, and they're both kind of in the same bigger valley. So there's like two little minima. Maybe one of these is the global minimum and one of them is the local minimum, but they're very similar energies, both in the same valley. And we call these things conformers. And a famous case of this is alkanes have trans and gauche forms. Have you guys ever heard of this? And those are different conformers. And so often we lump the conformers, the ones that are minima that are very similar, and don't really have much of a barrier between them. We just call them all together as one species. So this goes back to this issue, what's the definition of a species? So is the species this valley, or is the species this bigger valley that includes both minima? And people, it's a matter of your definition of which one you want to use, but a lot of times, if the two of them, the two minima are close and don't have much of a barrier between them, we just lump them together and call them one species. All right. When you're trying to work on these problems and get the thermo right, it's super helpful to find the global minimum of your atomic arrangement. And then if you can find as many of these other minima as possible, it's actually helpful. You can get more accuracy in your computations to do it. But you need at least one minima to be able to do what I'm talking about. Yeah?
Vibration later on, if you don't have the second derivative of the...
Yeah, well, wherever you pick, you have a minimum, you can always find close to it. You can do a parabolic approximation. Yeah, you can always write a parabola. Now, really, the real function might just be like this, and not look like a parabola. But you can always approximate it by parabola right close to the minimum. And this is what we're doing when we're making a harmonic approximation. We're like neglecting the cubic and quartic terms and stuff, which might cause this other, this is the real curve, the real V of R. And this is our quadratic approximation. Yeah. Yeah, that's right. Yeah. So you can see the kinds of problems you could get into sometimes, depending on what the real shape is. Sometimes the shapes are very deep valleys, and the parabola is actually a really good approximation. And some of them are kind of just little dips in a big flat plane. And then this quadratic approximation can be really lousy sometimes. And those are what we call floppy molecules, the ones where like really the thing can go a lot of different geometries with about the same energy. Whereas if there's like a very specific geometry that's very favored, then that's the quadratic way. The RRHO is better for that. All right, so back to the Taylor expansion. So we say, well, we're going to write V of R as V of R around our minimum. And then we're going to say, well, there's a bunch of second derivative terms of the Taylor expansion. The first order terms all vanish because we're at a minimum. Second order terms, we get the quadratic approximation. And then in principle, there's a lot of extra terms here called the anharmonic terms. And typically, most people forget it. They say, it's too complicated, I can't deal with anharmonicity, I'm just going to leave them all out. There's a subfield that worries a lot about these higher terms. And they definitely are real and they affect things. But to start with, usually people say forget it. Because it does make a lot more complexity. So now if I've got to this point, I just need to know this number of the energy at the bottom, and then I need to know this matrix of second derivatives called the Hessian of the potential surface. And from the Hessian, or something that's called the force constant matrix, the Fs. If you mass weight it, it turns out that the eigenvalues of this are the squares of the frequencies that you wanted. And so it's now simple. Once I have this matrix, I just do a little bit of linear algebra, and boom, I have the frequencies. Remember, the whole purpose here is I'm trying to get the frequencies because the frequencies appeared in my expression for the partition function, the news. Right? This whole calculation is done for you automatically. So if you type in the input deck of a quantum code, I want to have the vibrational frequencies, you just press go, and it does this whole rigmarole. It finds the minimum, computes the second derivatives, does the linear algebra, spits out the new I's, and also often will give you the Q's for the vibrational thing too. All right. Now, this is just a warning, and we just kind of mentioned it, is that everybody uses RHO because, first of all the code spit it out. So it's like a number that's coming in the output file. So if you're a lazy graduate student, very simple to just look and see, oh, there's the output. Okay, it says whatever number, I'll use it. Also, it's quite complicated to handle the floppy cases. So if you have a situation where your V of R cannot be fitted to parabolas, but instead has some really goofball shape, it's a much bigger headache to figure out how to figure out what the EIs are, and therefore what the Qs are. And so a lot of people don't do it. And so if they're honest with you, they should say, sorry, I can't tell you the thermo of this molecule because it's too floppy and I don't know what to do. But if they're not honest or they're not aware that they have the problem, they just read the output of the deck and it says, here's the quadratic approximation number, and just use it, boom. And they report it in the paper, even though it has no meaning. So just be aware that this is a problem. And this is most commonly happens when there's internal rotors. So if I have a carbon-carbon bond, and there's some stuff stuck on each side. Typically, when I rotate around this bond, if I rotate this group relative to this group, that motion usually doesn't have a high barrier, and it kind of looks like this, where you can freely go from a bunch of geometries that are all perfectly reasonable without really having much of a barrier. So this is the most common situation where you get the problem that the RRHO approximation is not accurate. And there's some kind of common ways that people try to deal with this. And sometimes they're accurate and sometimes they're not. And I say typically people use them without knowing if they're really accurate or not because it's hard to figure out what the real true value is. All right. And then there's another thing is that when we report the standard free energies, it's usually kilojoules per mole, right, is what we see in the tables. It's per mole, it's not per molecule. And so if you want to try to convert, we've got a Q for a single molecule, then we want to get the Q for a whole mole of molecules. The way to do it is to take the numbers for the single molecules and raise them to the nth power, and then you have to divide by n factorial because the molecules in a mole of gas are all indistinguishable from each other. So I can't tell one methane molecule apart from another one. So I have to call them all, I have to get this like factor that comes from statistics. Just like I had a statistical factor for the rotation of hydrogen, I get this other thing for interchanges of methanes. And when I do the math about this Q, it turns out that I can write the logarithm Q to be this way. And then V over N that comes at the end here is just KT over P. And I usually am doing standard states of P with 1 atmosphere, so I know what P is. And so I know how to do it, and I can write down the whole formula. And so this is how you do the whole computation. Yeah. This is all ideal gas. So if you want to go to non-ideal gases, then you need to have the non-ideality, and you have to have like an extra term like the van der Waals coefficients or second virial coefficients. And then it's actually not that hard to adjust this Q to correct for the non-ideality if you know the equation of state. You may not know it, and then there's some approximate ways to guess, but I would say you don't really know for sure for the non-ideal ones. But I would say for combustion, the higher the temperature is, the more the ideal gas approximation is valid. And so at the post-combustion temperatures, ideal gas is good for almost every case you'll ever get. Pre-ignition might not be true. And particularly for like liquid fuels like diesel, you might be in a case where you're like have vapor-liquid equilibria, and you have, if the pressure's high, your vapor might be very non-ideal. And so you can get some strange behaviors from that. All right. When you try to do these evaluations, if you remember back when I showed you translation, the Q for translation actually has the volume of your box in it.